Then you guys can see the screen, it's going to glare from these things.
Yeah.
Yep.
So we talk about learning models of projected actionable labels. So every few years I have a new favorite talk. This is my favorite talk. So hopefully you guys get excited about it also. The context, I think I saw a slide a few weeks ago. I've been involved with machine learning and AI for 40 years, and with machine learning applied to medical tests the last 20 years, and a whole variety, a whole gazillion different tests that I've been involved with wonderful medical collaborators that I'm fortunate to work with. But what's interesting is many of these discussions begin by the doctor saying, okay, Russ, build me a tool which, quote, does what I do, but better. Well, what does that mean? How can I know do what someone does, but better? As I started thinking about it, I realized I wanted to go back in time. Do you guys know this? Anybody's Wayback Machine? It's a little magical machine that goes back in time. And I'm going to go back when I was growing up in the 1980s. That was a day when expert systems were around. But here was a story that Mom truly told at that time. There's a patient. Does this patient have a manic depressive disorder? So the doctor says, okay, to find out, tell me his age, exact hand, and a bunch of different genes and a bunch of other things. Give me that information. And so we get the information from him, and the doctor then thinks about it. And apparently I've been told this is how doctors think, they do little spins.
I didn't know that.
And says, yes, the patient does have MDD. So that was the mantra. Many people did it. That was expert advice, but people said, well, gee, what about the doctors who aren't always present? What can we do now? Can we sort of calculate his knowledge? And so there's this expert systems that were designed to have developed extraction, which is not a painful process apparently. And it was like a rule-based system that then can try to calculate what he knows about the rule. And so the good news is it works. Sometimes the bad news is it only works if the expert knows the answer to this case and also can articulate it, can express information. And of course, the quality is only as good as that expert basis definition. So that was 1980s. Now let's go back in our time machine and go the other direction, to the 2000s. And supervised machine learning is now the new mantra. Same idea. We have a bunch of description of a patient. And a classifier is a tool that then produces the answer. Classifier is this computer program in general. But unlike the 1980s, where we had a human tell us what it was, we use supervised machine learning. And here we have historical patients that describe the same characteristics of the patient, but also the label, again, just as you saw from my lecture a few weeks ago, and you've probably seen many other times. And then machine learning algorithms are able to provide information, to take this information and encapsulate it in terms of the classifier. And again, QR code for the talk I gave 2 weeks ago here. But now let's look at this tableau, at this matrix that describes patients and features and outcomes. So one thing is, what are the features you use and what are the distribution of instances? I'll say a bit about that at the end. But I want to focus on the label. What should the outcome label be? And also, what should the true values? What is the truth for those labels? How do you get those? So I'm going to talk first about this thing. What should these values be? How are they determined? And perhaps the answer is just what I said. Do what I do. Get the doctor's insight. So let's imagine that at training time, I have a bunch of data. Here's 3 patients. And I asked the doctor. He says, that's pretty obvious. Yes, MDD, yes, and no. Yes, no, and yes. It's obvious, I'm done. There's the answer. But then you say, but maybe I should get a second opinion. Here's another person who says, I'm not so sure. And there can be disagreements here. So that's a problem. Now, if that happens, then, well, which doctor do we use and how do we decide? And all these questions come up. But of course, this is saying doctors disagree. Does that happen? Well, you know what kappa scores are? Kappa scores are agreement. So if I ask you about what movies you like, and we like the same movies, and he goes kappa of 1. If every movie you like, I hate, that's kappa -1. If you might as well flip a coin, it's kappa 0. It's agreement. So what are the kappa scores for things like depression? And it turns out it's about 0.32. One means you agree. I mean, this is amongst practiced clinical clinicians. They disagree, a third-ish of the time. It's a little more complicated than that, but there's not universal agreement. Well, that's a bummer. But what about other diseases? Alcohol use disorder, 0.4, and I think and for mixed anxiety depression disorder, 0.06. I mean, there's a lot of disagreement. Doctors don't agree with each other. Well, that's psychiatry. That's I won't say flaky, but it's a very subjective thing. Something concrete like pathology scores. I mean, that's pathologists looking at things. And Kim says, of course they agree completely. No, they don't. 0.35, 0.46. I mean, these are not horrible. They're not zero. They're not negative. But they certainly are not numbers that say two clinicians agree all the time. Not even close to that. And now, if experts disagree, which one should you use? The one who is the most senior one? Or the one who speaks the loudest? Or the most recent literature?
Yeah.
It's even worse. You ask the same clinician on Monday, and he says yes, and the same clinician with the same data says no later on. So if you ask the clinician on Monday or on Wednesdays, I mean, again, it's a real problem. So maybe do what I do is problematic. So how do I make it better? Well, why don't we try to have a label that doesn't depend on a subjective clinician's opinion? Based on some objective criteria. Think about it saying a kappa is like 1. How do we do that? Well, first, let me give you a definition. I'll say a label, an outcome is objective if there's an unambiguous way to determine or to verify its true value. So, for example, hyperglycemia. Right? There's a blood glucose measurement, and by definition, blood glucose less than 3.9, that's hyperglycemia. And again, I'm assuming people can read the measure and it's not broken, but assuming all the standard assumptions, two clinicians looking at that will say, yep, it's 3.8, right? It's hyperglycemia. Done. Being overweight. Again, a BMI between 25 and 29.9. You take a patient's height, you take a weight. Hey guys, you have a scale, and again, assuming the scales aren't broken, if you look at two clinicians look at the same scale, would agree on the same weight. That's unambiguous. Or maybe, let me ask people in this room, who thinks arm is broken? Yes? No? Yes. It's not always true, but in many cases, they're an analog measure. You can look at it and say, yeah, this is universal agreement. I think every doctor and every human being who understands how to interpret these images, understand the image or would say yes. Again, not always, obviously. I'm sure Kim has lots of stories where it isn't so obvious, but in some cases, look it up. So now, I just said a label is objective if you can just look at it and see the answer. Well, that suggests that just observations are enough. Or computations, like the height divided by weight squared or something like that. Or just see if it's bigger than 3.9. All those are standard approaches. If that's the case, if objective means observable, why are we doing this? Why should we bother learning a model which estimates a label? If I can just look at it and read it off. Well, let me answer that question. I'm going to describe 4 standard situations that define four different classes. Objective label now, objective future with an action, and objective label for best action. And we're going to focus on the last 2, because that's a critical part. But I want to introduce it by talking about the first ones as well. So, off we go. Objective label now. So I want to know the patient's current status, and that might be useful. Think about situations where there's an objective test which is expensive or painful or risky. Maybe I want to learn a predictive model that estimates that in a way which is cheap, painless, or risk-free. So for example, adenoma, right? Those colonoscopies, even if they're perfect, they are expensive, they're painful, there's some risk. By contrast, our colleagues at MTI, the Public Technology Incorporated, have PulpDX, which is a tool where you pee in a cup and there's analysis. It's cheap, it's painless, and it's risk-free. So it might be an approximation, but it still might be worth using in spite of that. This is Kim, I expect you to do it. This is I don't know what it is, fortunately. There's biopsies that can determine fatty liver, but my colleagues at now Echo have a tool that uses ultrasound that can look at a liver and a cheap, painless, risk-free method and give an answer which is a good approximation. That's one situation where I want a model that can estimate an objective label quickly, be objective about doing it. The next case is even more obvious, right? Objective label future. I want to know the patient's status later. So for example, I want to know a person's weight in 30 days. So in 30 days, I can watch a patient. 30 days later, I can say, yeah, there's the weight. Done. And it's objective, but I don't know it now. But there's an objective test, I just have to wait 30 days to find it. Or one's A1C, they're back in 3 months. Same thing, I got finger pricks, I can measure it. Or maybe the Beck depressant inventory in 8 weeks. So I want to determine measure psychiatric disorder. So these are objective labels in the future. Now one variant of that, is the subtlety, objective label future action. So I want to know a patient's weight in 30 days if he's on the paleo diet, or someone's A1C using a specific combination of carbohydrate ratio and correction factor, a certain regimen, that's what we call it. Or someone's BDI score if that person takes SSRIs for the next 8 weeks. So that's objective label future when I specify the action. These are three ones that are pretty straightforward. The most interesting one I want to focus on is future action, objective label for best action. What is the best action to take for this patient? So I want a model that returns the action which is best, so I can decide now about an action that has an outcome that I can measure in the future. So what's the best weight in 30 days? And it could be paleo, Mediterranean, vegan, or no diet. Which one is best? Our best A1C with carbohydrate ratio correction factor being several different settings. Or the best BDI in 8 weeks with a selective serotonin inhibitors or ketamine or cognitive behavioral therapy or whatever it is. And his answer is vegans are best and this values in CBT is correct for this patient. So this is an objective label best action. And it turns out it really isn't objective, but we have this tilde to explain it. So a quick summary of the 4 things. Objective label now, here's a patient description, and what's the patient's weight? 3 and 42. Objective label future is the same patient, I want to know the weight, but now I want to know the weight in 30 days. So I can answer it. Objective future action, I specify the action also. And what's the future weight of this patient with that action in 30 days? And finally, objective of best action is given a patient, find the action which is best, for example. Is this clear? So a quick outline. I described expert systems, described machine learning as a foundation, and now I get to the fun part. Right? I talked about learning models to predict objective actual labels. I'm going to talk about objective labels first. And then we're going to use actionable. Now, the 4th one, objective label best action, is the actionable decision. I'm going to focus on that. Some issues and some conclusions. So these are very straightforward. Then I get some more complicated things over here. I'll see how time allows for that. So objective labels. I talked about the 4 types. I'm going to say a bit about objectivity and give formal definitions of the associated learning types. That's how to get the data and what does learning mean in this context. So objectivity. So remember I gave this definition. Objective labels. A label is objective. It is an unambiguous way to determine its value, independent of the observer, as opposed to versus non-objective, subjective. Judgment-based interviews or interpreting pathology slides. And so we said, yes, this is objective. I can read the measurement. This is a pretty obvious image, and sometimes it works. But then I mentioned this other one here about a self-administered test. What do you mean, Russ? How could that be objective? that's a patient's opinion, isn't it? Let me define what I mean. So let me compare the veracity of two statements. Oops, sorry. So one claim is P equals NP. Do people know about, do you know about NP hardness and things? So this is a statement that people have spent decades researching, we don't know the answer. I'm Russ, by the way. I just said P equals NP. This is a very different statement. Right? This is one we don't know the answer to. You just heard me say it, right? So the answer to this question is yes, because you both, all three of you heard me say P equals NP. So let me compare the veracity of Fred is sad versus the claim Fred said, I'm sad. Again, these sound similar. This one, you know, a psychiatrist might try to take notes on this. With this, if all three of you in the room, and Fred on the couch says, I'm sad, did Fred say he's sad? No. So this is unambiguous, right? All English speakers could hear him say that and believe it. Do you know about soap? Is that a term that is? So there's a term of soap which is, well, if you knew about it, my wife's a clinician. She said this exactly backwards, but just want to point out, when I say objective, I mean clinician objective. I mean, two clinicians will agree objectively. I'm not saying the patient is telling the truth. The patient might be lying, might be trying to play games. I don't care. The whole point is the clinicians agree on it. So this is clinician objective, even if it's patient subjective. You know what soap is, it has the exact opposite meaning. Don't worry about it. Okay, so that makes sense. So I'm going to say that a self-administered survey, a self-administered questionnaire, that would be objective because two clinicians will look at it and say, you said 7, 19, yes or no. Okay. So instead of asking these clinicians, I would change. I would say, I'm going to say, use an objective measure. Let's see. Given this test, does the BEI score is greater than 10, yes or no? And it's unambiguous. Two clinicians will agree. Now, I'm not saying the BEI test is correct, but I'm saying, given this as a standard, I can say, I'm going to redefine the word depression to mean the self-administered BEI score is greater than 10. Unambiguous. Okay, so that is the issue about objectivity. Now, I talked about, this is what the true answer is, what does a learner do? So I do learning research, right? So what would it mean to have a learning model that does a good job? It's probably what you think it is. For objective label now, the truth is a function that's patient to a label, to some value, which happens to be a real value. A learning tool tries to find a model that takes the same patient data and returns a number which is similar. And again, it's L2, for example, or whatever it is. It's just something that, you know, if the answer was 7, I get the answer 8, I'm pretty happy. If the answer is 7, I get the answer 22, I'm not happy. So that's what a learning algorithm try to do. I want to minimize that. Same thing, same idea over here. So I want to measure some different number, but same idea, I try to minimize L2 loss. For the objective label of future action, notice now the input is a patient and an action. And there's a set of allowed actions. There's something to specify that there's a set of values here that can be possible. And given a patient action, it returns a real value. And again, I try to build a model that takes two arguments, a patient and action, and tries to minimize L2 loss. Okay. No surprises there. So that was the first 3 of them. Now you might say, but Russ, you didn't tell me about objective label best action. Yeah, that's the fun part. We're about to get to that. Questions so far? Okay. So I want to motivate why I want to do it, give formal definition, give an example of it, talk about this idiosyncrasy about having a vector and objectivity of that. So off you go. So as of now, I've solved machine learning. I've just said I can give you a diagnostic label for what it means to be depressed, it's BDI greater than 10. I can build a label dating set, a label training set, and use that log to diagnose a novel patient. Ta-da! And now, the patient's got MDD, and I want to treat the patient, right? Well, I can give SSRIs, SRIs, or ketamines, or maybe it's therapy. I can give cognitive behavioral therapy, or electroconvulsive therapy, or combinations. What's best? It makes a difference. Different patients respond to different treatments. Only about 50% respond to any single depression. So this poor patient is diagnosed as depressed, and then the doctor says, here you go, here's SSRIs. 6 weeks later, oh, sorry about your weight gain, it didn't work. Let's try this one, I'm sure it's going to work, Oh, sorry about impotency, try this other one. It keeps going. Why are we doing that? Why do we give a diagnosis if it doesn't identify the treatment? As a doctors right now, we do better. So I talked about true values, the labels. Let me now talk about, and this should be objective, what should a label be? So instead of who is MDD, let's change it. What's the best treatment for the patient? Who should get SSRIs? Who should get cognitive CBT? Let's talk about that now. So here's the same situation. There's a patient. What treatment to give? And again, you ask this doctor, you get an answer, and this doctor doesn't agree completely. Now what? Well, what should we use? The same question, get an old guy like him who's very loud, and he's going to be dominant, but maybe why don't we instead ask not what do doctors say, but what should they be saying? What is the best treatment? So let's define a label in terms of the action's effectiveness. So you can imagine, for example, there's treatment there, and we can now talk about the score in 8 weeks. And again, this is what objective label future action talks about. Right? Let's say, given a patient an action, what's the score? And again, I'll give the numeric score for that. And now, what's the best treatment? Well, I don't know. I mean, that's one treatment. What about the other treatment? Which have in I want the most effective treatment. So here I want just a particular treatment, what's its efficacy. Now I want the best action, best in terms of a set. So let's imagine, look at the animation. Imagine I was considering just 2 options. And now imagine I've solved issues of selection bias and counterfactuals, and I know that this patient with cognitive behavioral therapy would have gotten 14, and this patient with CBT would have gotten 6, this patient with SSRIs would have gotten 12. If I knew that, then I could determine the best one. I want the treatment which leaves the patient having as low a score as possible. So he gets SSRIs, he gets CBT. Make sense? Now there's some subtleties like, why do you see SSRIs? Well, because 9 is less than 14. And I want smaller numbers. Okay, so it's easy. Okay, so, do you guys know comic book guy? No, the Simpsons fans? How much Simpsons? Oh, you guys are missing it. Comic book guy's a character on the comedy show. So, so I did that? So, okay. Did this thing. Okay. So there are several treatments you can consider to try to lose weight. I want his weight to be as low as possible. So I can imagine I could solve selection bias and counterfactuals. I can get his weight in 8 weeks. And now the best answer is paleo because, well, I want to lose as much weight as possible. 225 is less than these 2 numbers. But that requires, again, having a preference, which, again, by coincidence happens to be the smallest number. So I really want the smallest number. Careful what you wish for, right? What about starvation, right? So maybe smallest isn't quite what I want. Maybe I don't want to die in the process of doing it. But you can imagine this issue. But you have to say, what are you really looking for? Come down in a moment. So what was my goal for a formal description of performance system? I did these 3. Let's talk about this bad boy. For objectively the best action. Here, I can start by saying imagine I have the truth. The truth is basically the objective of future action. It takes a patient and action returns a value, some response, some new world of the truth. So I need to have that's what happens next. I also need to have a value. How good is it? How much do I want at that stage? Is that a good state or a bad state? That's different than saying what the weight is. How good is that weight? It's driven the same with the BDI scores. How good is that BDI score? So given that's a function, I can now talk about the response, the objective label, best action response, is the argmax. I want to consider all the actions, for every action I can compute, the world I come up with if I take that action in that state. And then the value given to that. That's a real value. It's a real value. And I want to try to find the thing which makes the value as large as possible. Does that make sense? I need an evaluation function, which I notice the other three measures didn't have that. That's the only time I care about the quality of the answer. So I want a G hat to be similar. So for example, I want to evaluate a proposed model by saying it's the one whose value is as large as possible. Over the distribution of instances I see, I take the actions prescribes, I compute the value for that, and I'll make that as big as possible. I want to optimize that. And as you think about action, I'm looking at how much worse I am than the best possible, but don't worry about that. That's a small issue. So, here's comic book guys with a little example of what's really going on and how do I evaluate it. So there's comic book guy, and there's 3 diets. Guys, have a comic book guy. Talk about a wasted youth. So there's the diets. And again, imagine this is God's shoe. This is his weight in 8 weeks if I do that. And now, what's the score? I'm going to define the value as being how much weight he lost. He lost 15 pounds, 5 pounds, and he gained 5. He lost negative 5 pounds. And now if I ask you what's the best action, well, what action really is the best action? Who's tracking? No diet? Paleo? Paleo? So the best action is for this. I lose 15 pounds. I mean, he loses. That's the winner. Questions? It's pretty obvious. If you know the truth, it's easy to know what to do next. Now, let's imagine, again, I'm trying to maximize the weight loss. And now imagine on my future action, objective label, future action, it came up with these scores. So these are scores that it thinks it's going to gain 12 pounds and lose 20 and lose 1. Imagine this is my incorrect model of the world. How good is this model? So first question, given this, what action, if comic book guy believed that, what action would he take? He thinks this is a world, and he wants to take the action which makes this value as large as possible. So what action does that? Yeah. It's vegan because his incorrect assumption about the world says that's the best thing to do. Now, how good is that? Or how bad is that? Well, if you think about it, he thinks he's going to lose 20 pounds. He actually only loses 5 pounds. Okay. So the score for this action is actually 5. But how much worse is that than he could have done? If he had done paleo, he would have lost 15 pounds. So this is like 10 pounds worse than he could have, than he should have done. How do you know the truth? Okay, just a little small example. Things weigh 220. He really weighs 235. So we use the true value to actually estimate the quality of the response. Okay. Okay. And this is just sort of mathy stuff. So the same thing I just said a moment ago. It's worth just observing that I want to use the decision that's made is based on the incorrect model, but the way you evaluate is based on the true model. See how much worse you did than you would have done had you guessed the right answer. Okay. So I covered an example and formal definition. Let's talk about another subtlety, another real issue that clinicians will have to deal with all the time. So again, here's that patient, here's John, and SSRIs, you can measure. So NPD is associated with many different factors like suicidality and anhedonia. So again, I can measure just suicidal thoughts, but in fact, this BDI and other things actually measure several different things. Let's imagine I just have despotize it, just 3 of them. There's suicidality and anhedonia, a scale from 0 to 5. And there's also side effects. Drugs often have weight gain and things which are not desirable. The whole point here is the output to the objective label future action is not a single value, it's a vector. This is what happens. This is the profile of what happens with SSRIs for this patient. And so it's a 3-tuple. And in general, a drug's effect could be, there's drug efficacy, there's side effects, there's also cost and the time it takes to take effect. It's a complicated thing. It's a vector that describes the outcome. So now, let's imagine, I also say about ketamine and CBD. So here I can say the future, the objective future of actions, this is the truth. For John, ketamine is this vector, and that one out. So this could happen, right? 3 different treatments, 3 different responses, 3 different descriptions of what happens. Now what? So now what's best for John? So is 202 better than 125 or 340? What do you think?
First one?
The first one, why?
Because the score is like lower.
But maybe John doesn't care at all about weight gain. He doesn't care at all. No, I can make other numbers up. But you can. But the whole point is, why should you decide? I asked you to, but remember I had an evaluation function, which I didn't define. It's going to be some function. So for example, John might say, I hate the suicidal thoughts, and I hate anhedonia. I don't care about weight gain. If I gain weight, I don't really care. This is my evaluation function. So I take these 2 numbers and return a single value. So for me, for John, suicidality is 3 times worse than anhedonia, and weight gain is not an issue. There's no that. He would say this is a score, and he would say SSRIs, because that's the largest number, the least negative number. So that's John's opinion. John's mother says, no, I see John. These are all bad. They all count equally. They all count equally. So now, what would John's mother say? Well, she would say that the best thing, that mom's value function of John with action would be ketamine, because again, it gives, each add up, just as you did a moment ago. But the point, I want to point out that this is assuming they're clairvoyant, they know what's coming in the future. There's no ambiguity about these numbers. It's just how good is the world you live in those situations. I'm not talking about errors in measurement or not being able to predict correctly. I can predict perfectly. It's still an obvious way I should do this. This valuation function is critical. It says what's best in terms of the quality of any proposed other measure, because again, we have to have the expected value for that. And this valuation function can involve life, probability of life or death. It can involve the dollar cost, quality adjusted life years, whatever you want is embedded within this. It should be objectively computed, and it should be a real value. Because again, if I compare 5 to 7, I know it's bigger. If I compare 19 to negative 203, I know it's bigger. If I compare Jupiter to Saturn, I can't compare it. If I compare 379 to 419, 203, it's got to be a real number. Like I can compare them. It can't be nominal. It can't be a vector. And another point, doctors. I tell doctors all the time. Okay, Russ, you tell me what I should do. I say, no. You're the doctor. You're the person seeing the patients. You're the person making the decision. You decide. You tell me the objective value. I'll try to optimize it. It can vary from hospital to hospital. It can vary from patient to patient. That's fine. But to be precise, someone has to say what the valuation is. My job is to predict what the world looks like after you do this treatment. I try to estimate that. Your job is saying, if I have this world, that's better than that world. Is that point clear? Again, this is a point I'll mention a few more times. All right. So off we go. So the final point I want to say this is the word objective. If I tell comic book guy to take the payload out, he can take the payload out, and then I'll wait, I say 6 weeks, 30 days, I can then measure his weight, and sure enough, I said it'd be 225, it is 225, I can say I got the right answer. I can say that this is, that I was correct with the future weight and the value. Again, I'm assuming that the function and the evaluation are both objectively computed, is objective. But remember, I want to find the best value. Best means best. It means I compare this value, I compare this value to other values. So now here's a problem. I need to know that comic book guy with vegan and comic book guy no diet both weigh more than 225. Now the problem is, John's comic book guy is one person, he took a diet, and that person's not around anymore. What would have happened had he had the other diet? I don't know. I never will know. Maybe I said something over here. Now, why not have comic guy try vegan and then go back and then try no diet later on? Well, first, if there's a 2-year delay, he's a different person. He got married, he goes to the gym twice as often. It's not the same person as he was in 2022. And again, I lied, we don't have a time machine. And I said we did. So we can't go back and pick the same guy later on. So we can never find out. This is probably counterfactual reasoning. We know what happened with this treatment. What would have happened with that treatment? We don't know, we never will. That's why he gets that little tilde there. Did you say? That's interesting. Okay, so that's the end of the simplified version. There's now 4 issues I want to cover, and at some point Kim will say, shut up. I got my time, right? So, there's issues about objective label, best action. One is, I just mentioned, I want to objectively show this is the best action, but I can't because I don't know what happens for other actions. Well, there's distribution of the objective or average treatment effect. I'm going to talk about that. Another issue is sampling bias. And as I'm learning, I have to have some idea about what happened under this distribution. I'll talk about issues with that. And the answer to solve that is something called randomized control trials. Another issue people always say is, gee, Russ, that's great for a clinician examining a patient, but why would we actually ask about a lab test or genetic testing? How does that fit into it? Turns out we talk about policy sequence of actions. I'm going to talk about that, multi-step actions or policies. And finally, once I have these extended actions, how do I evaluate it? There's some subtleties there. We'll talk about expected costs. Okay, we're all set. Any questions so far? Tracking? Let's talk about this objectivity issue. So I want to estimate the expected value of a comic book guy. So there he is. Again, vegan. I can measure his weight. I can compute the value for that. All has been done. Now imagine in your mind's eye, he had a bunch of identical twins, octuplets, right? And every one of those, I can now do like an RCT and just randomly assign them different treatments to people, and they get answers, and I look at the value. And now I can say, let's take the average value. This is the average value of comic book guy in different incarnations. With vegan, the average score is 5, and with paleo, it was 7. And so now I can say, well, gee, paleo is obviously better, because 7 is bigger than 5, I want to maximize it. So the R max in this case, with paleo, because that's 7 is bigger than 5. Make sense? And so, again, one goal we look here about there's a truth and a value. I can talk about what's best for a single instance, but I can consider the population of instances and talk about actions over that. And then try to optimize that. Again, I'll come back to the moment. I'll talk about the expected value over the distribution of instances. So again, we can talk about that. This comic book guy, if I consider men and women, old and young, with different diets, and again, the same sort of thing, we're gonna just randomly assign them. And again, we're gonna compute what happens at the end. We're gonna define the values, how much they've gained or lost, compute the expected value, and the same thing we did earlier. You know, we got the argmax of this would be vegan because 5 is greater than 7, greater than 3. So now, over the population, what's treatment best for the whole population? That I can do objectively, well, in the limit. See, there's people, that's going to, if this is done manually, with no confounders, so I can say in the limit, this is right action. So now it's getting towards objectivity, not for comic book guy, but for the population. So again, I've got a set of actions here, there's 2 actions. I compute the expected value, the distribution of that action. So, so we have 2, I'm going to collect the sample of size 4 in this case, drawn IID, independent identity distributed from the distribution, run action I on SI, and so and with the expected value over the set of 4 instances, with the expected values, score for that, take the argmax over that, and then say everyone's going to take the action B. That's the right set of 2 pictures. Make sense? A little bit of mathy stuff. And as the sample size gets larger and larger, this will converge to the expected value of that action in the population, because the sample just approach the truth, which means the argmax of this will be the argmax of that. That makes sense. So find number of actions. And these are objective, these are objective also. So that's what I said. This is an objective-ish version of this. This is average treatment effect as opposed to individual treatment effect, but again, the same idea. I'm going to go back to the point about the number of instances I need. So again, I'm thinking it's best for the population, not for the individual, and just realize that in general, even a single act can be stochastic. That doesn't matter. Next issue, sampling bias. So, the objective label now, the objective future, both require estimating the value of a function over instances. And it's easy, you just observe the training data. The training data is from the same distribution as the testing data, and as I get enough samples, it's going to be right. It's unbiased estimating. And objective future action is also easy. It requires drawing an instance of a patient and an action from the distribution you care about. And that's going to be an accurate and unbiased estimate. So all well and good for these 3. Unfortunately for this guy, for objective best action, requires estimating f of xa for action distribution, and maybe it's twice as many men as women, that doesn't matter, because we're testing the same thing. But I want it for all A, not just for the one that was experienced, the one that came in observation from the observed set. We only get one A, we don't find out the other ones. Which means that at least selection bias and counterfactuals, so all the other issues I mentioned earlier. So remember I showed this slide here, but I need to draw from the distribution. So what can happen? So let's imagine we have observational data. Imagine the doctors have this, are told for 18-year-old patients, use the red treatment. For under 18, use the green treatment. And here's the data we observed. I want an outcome up is good. So this data, that's treatment A, green, that's treatment B, the red. And now, if I were to say, which treatment is best for everyone? Well, it's easy, right? I can look at this, the average here is, the green is higher than red. So we're done. On average, you get the red treatment, right? Because it gives a higher value, it gives a higher value of the people you observed. But there's a problem before you try to anticipate the problem. I have a bias sample. The sample isn't drawn from the whole distribution. Green patients, only patients under 18 get the green treatment. And only patients only over 18 get the red treatment. If I were to, so that's why it's a bias sample. I'm drawing from the distribution, which is not the overall distribution, but it's a subset of it. What if I did the right thing? I gave everyone everyone had, both old and young, got green or got blue, got red. And now the data looks like this. And now which one's better? It's pretty clear that reds are uniformly better than blue. So treatment B is better. I said treatment A was better earlier, but now treatment B, if I have the whole population, it's obvious that treatment B. And that's just because, over the whole distribution is true, just observing that the distribution with respect to the sampling distribution is not what I really care about. I'm just pointing out that these distributions are different, and so that's why I expected values to should be no surprise. This is a randomized control trial. You guys have seen it, right? That's why you do RCTs, so it's in the bias. Next one. Questions so far? So on to multi-step actions. Let me introduce this slowly. Remember, the truth is, the Rmax is the action which the guy who's the best with the distribution. So once I know that action A is best for old men, young men, for women, A is the best treatment. Vegan is the best treatment. But what if I want to think about different treatments for different people? Let's consider maybe paleo is better for men, but vegan is better for women. Maybe. So it's talking about a policy like this one. Ask about the person's sex and then decide based on that. So I can do the same thing. I can have three different actions. There's everyone's vegan, everyone's vegan, or I make this decision about what they should get. And now, again, I got three policies. I can now draw a sample, a sample size 4 from the population, and then from that sample, I then run that action, the ith action on that sample. And then evaluate it. And here I see that the average for here was 5 and 3 and 6. And so I take the Rmax, as I saw earlier, so given this set of 12 individuals, 3 times 4 individuals, the best action is in fact this policy. So I can do this, right? It's all the same framework. So a single action, it's a conditional action. You guys know reinforcement learning? You see the word policy? So this is a very simple policy. Operationalize it. You can just take this and make decisions about who should go which diet depending on the sex kind of person. But you can imagine more complicated things. You have a whole neural net that made a decision of who gets which one. But again, that's one of the options. You consider all gets vegan, all gets paleo, and now there's a more complicated. You can just run that every time for a sample and see what's best. So that's the idea. So that's an action coordinated steps to get information about the patient. But also, that was trivial, but what about a pathology report or an imaging scan, genetic testing? Again, I send the clinician sends the patient to a genetic counselor to get genetic testing, to get information. And why is he good? That's not objectively evaluatable. But the policy that includes sending to that person, getting feedback, and using that's in this framework of objective decisions. So treatments. So it's a policy in the reinforcement learning vocabulary. I'll go a bit faster. There's a whole bunch of issues here about how you do this, and you can imagine that the outcome is going to be, we've never had vector outcomes, right? So here's a vector, the sex as well as waiting for 4 weeks, and you can use that. So another situation, like a screening test. So I could have the diagnosis test, I run a diagnostic test. If that test reports negative, so the patient's fine, you don't do anything. And then a month later, either the patient is fine, as we thought, or the patient's sick. Alternatively, if the test says the patient's sick, you then apply a treatment, and the treatment always works. So this is another situation we have a sequential decision process. I do a test, and depending on the outcome, I branch and make different decisions with different subsequent sub-actions. So recall again, the function itself, there's 3 different outcomes, because remember, after the treatment, always cured in this case. So So I can have policies, which I try SSRIs, that is work, I try high dose SSRIs, that doesn't work. I then try SNRIs, that doesn't work, then I say, I can't help anybody. So you can sequential. This is like the diagnostic where I try to test as well as treatments. So sequential policies, you have a lot of time goes, you go into screening, followed by diagnosis, followed by treatment. So all sorts of tools like that. You have information gathering processes, additional ones, or maybe things that extend about treatment as well. So all these are okay for you. There'd be many agents. The general practitioner is geneticist, pathologist, radiologist, information about the patient, and make decisions. So it's all the same framework. So you can imagine, I talked about this deep neural net that did something, or maybe having a couple of things, but it sounds like if I want to try like 5 different tests, I can imagine like 5 factorial possible orders for those. Just, I don't know, spend that much time on it. But if you're willing to, if you tell me a causal model instructor, like you tell me it's naive Bayes or noisy, or I could do the test, I could just do one set of statistics, and then I can decide about n factorial things based on those computations. Does that make sense? So, final point, evaluating with these actionable models. Remember the example I gave earlier about this one here? You do a diagnosis, if it says no, you stop, oh, you the test. And now what's the expected cost of doing this? Well, imagine I have costs. Before I start, I know that if you're sick, it costs $2,000, not being sick is $0. The diagnosis test costs $100. The treatment costs $500. Okay, that is it worth running this process? Well, it's not working. I don't know at the beginning. I have a causal model here. I know that in this population, 60% of the people are sick initially. Of the people who are sick, the diagnostic test is correctly reports they're sick 95% of the time. If they're not sick, if they're healthy, it reports they're not, that they're correctly reports they're not healthy 90% of the time. But there's 5% and 10% chance of making mistakes or false positives, false negatives. Again, the assumption here that after a person who's diagnosed as positive, given a treatment, there's the chance of being sick is 0, but they're cured. So if I have this framework, I can then ask, what is the cost of this test? So if the patient was so it's all the paths. The patient, if the diagnostic test was negative and the patient wasn't sick, it's a true negative. That's one path. The chances happening with these numbers is 0.36. That's the chance that the patient really was not sick. 0.4 times the chance that if he wasn't sick, he reports he wasn't sick, it was 0.9, and so that's 0.36. So what's the cost? Just the cost of diagnosis. What about this test? If that's a diagnosis, it says negative, but it really was sick. Well, that's the probability he was sick, that's 0.6, times the chance that he was sick, but reported negative, and that's 0.6 times 0.05 is 0.03. So what's the cost of this? Well, $100 for that, and $200, $2,000 because you don't want to be sick. And what about this one? What's the chance that the patient, the diagnostic test said positive? Well, he might have been sick or not, regardless of what it is. And so you just look at the probabilities. Turns out that it's 6.61, so it adds up to 1. Three options. And the cost of this is 100 plus 500, $600. So the total cost of this process, of these numbers, is $465. So that's what this costs. Another option is just give everyone the treatment. So what's the cost of this? Give everyone the treatment. So it doesn't matter, there's no tests, everyone's helping you. So is this cost effective? Okay, about dollars. Yeah. So again, if I have a causal model, I get some statistics about the role and get answers. So if I just wrap up. Okay. So this is like a reinforcement policy. That's weird. Okay. All right, and I think which ones? Just some quick comments. Like, you can look at the formula just by doing just a little bit of algebra. And that's the expected cost of the population of this treatment depends on all these different things. Some things which are based on the diagnostic tool. What's the cost diagnostic tool? And what's its efficacy in terms of true positive and false and true negative rate? And things about the world, right? How bad is it being sick? How bad is it? What's the cost of treatment? And what's the prior probability spread about the world? How many people who get this test are going to be truly sick? And you can look at, for a fixed environment, you can talk about different diagnostic tests here and how well they work. You can talk about environments. It's easy to play little games. You can talk about two different tests here. The one I showed earlier, which costs $50, it's different, which has this treatment efficacy and has that treatment efficacy with different costs. And you can compare which one's best. From environment, the one we had earlier, turns out that the best one is the first treatment, the first diagnostic. And if you change other things, you get the other diagnostic. So let's get the details. Just it depends on the test you run. It also depends on the environment which you're going to run and the cost. So, there's also many measures. So I talked about expected cost. And you guys know about AUC and about zero and error things. Lots of others you can measure. Expected cost, right answer. There's other two costs. As soon as I do the correct model, I'll just wrap up here. Let me just jump quickly. So, summary of these 4 points. I want to objectively verify its best, but I can't. I can use trick. So, individual treatment effect, I can talk about average treatment effect. Sampling bias can happen. But if you do RCT, then randomize it, that solves that problem. You know, selection bias. Cost of intermediate, getting genetic testing and so forth, multi-step actions to look at. And if I had to evaluate it, talk about having this expected cost. Okay. Let me wrap up a few final points. So I began to talk by saying there's 4 different things I talked about, but I just focused on this one. But these 2 are just sort of introduction. But how do I compare objective level best action, objective level future action? And the answer is, it really depends on this thing. So notice, this guy doesn't depend on the evaluation. It just depends on the world that comes out. So if there's a single universal value, what's the probability of saving life? All I care about, forget cost, forget side effects, forget quality, all I care about is that. Then you might as well just learn this guy directly. But what about situations where there's many of them? There's 7,200 different possible evaluations. I talked about John versus mother. I talked about different environments, which I might apply a diagnostic test. I could just learn this one time, but then different models, I could then apply the different valuation functions and see which one's best for Edmonton versus Calgary, or for John versus mother, or for just repeating that John's model was different. I could just send one model here and then apply differently here. Use. Depending on the world I live in, I can make different decisions. Once I know the basic statistics, I'm done with that. Okay. Future, right? So I focus on these 2 issues. But what about the features? What features should be used? Might be from other agents. Okay, I'm going to skip this part, using it. You can imagine the future values. It would be nice if these are unambiguous, but it doesn't matter. Final few points. I started by talking about do what I do. clinicians saying that. What's the advantage? It's very intuitive. One of Kim's residents, I follow him around, just do what he does. I'm going to be an expert on that. It's intuitive, it makes sense, it's part of the apprenticeship program. It does not require data. It just requires Kim, or someone like him, to give all the expert advice. And it does not require explicating the value function. That's one characteristic. What are the disadvantages of do what I do? Well, only as good as the expert, and not everyone's as good as Kim is, so I found the wrong guy to solve problems. And also, I think it's wrong not to identify the evaluation function. What are you trying to do? If I want to apply in a different environment where this test is twice expensive, or this, where the treatment is twice expensive, or the repercussions of treatment are valued differently, if I had the value function explicitly, I can say this is why Calgary does this and we do that. It's the same test, the same outcomes, but we value it differently. Or this hospital values it differently, or the health authority values it differently. So having this explicit value function, I think, is critical. And it's not done very much. So how to operationalize it? So what should the label be? The way I view it is when doctors say the question, I say, quote, why do I care about this? Or rather, why do you care about this? How you use it in decision or action. So, does a patient have depression? Where is a tumor? Does the patient have stroke? Forget those questions. I don't care about them. Not this patient has depression. Should this patient get SSRI? That's an action we take. There's a tumor. I mean, tumors, they have edema and enhancing rim and then the chronic core. Who cares? Tell me, I want to take an action. What area should I irradiate? What body should I irradiate? That's critical. Does the patient have a stroke or a TIA or something else? I don't care.